Hi there, Satchel. This is Mr. Sand, and I'm here to answer your questions about the review. So, the first question you had was your first and third questions are about the same, I think. It says, what equation should I use for each problem, and how to pick equation in reference to each problem. And I think another one that's related to that is, what are some ways you can figure out how to solve problems with their word problems and create an equation? Well, there's only really for this whole unit here in forces, there's only really two equations that you use. One of them is F equals ma, and then there is the friction force, which is this. That's the coefficient of friction times the normal force. So those are the only real equations that we use, but you use them in all sorts of ways that we've been developing throughout the year. One of those ways that we use this is through vectors. So all forces are vectors. That's something to remember. Are vectors. That means, what does that mean for vectors? All of them have a magnitude. All forces have a magnitude, so there's a certain amount that they have, and they have a direction. Okay. So whenever you're given a word problem, you think about what the object is. You think about the forces that are acting upon that object, and then you write down everything that you know about this object. Sometimes you have to be kind of clever with that, and then you try to figure out a way to get to the question. Okay, so I guess the first thing you need to know when you're looking at when you're approaching a word problem, I hope this is helpful. The first thing you need to do is you need to just draw the scenario. That's the first thing you do whenever you're given a word problem. Draw the scenario with the force diagrams that we have been drawing for a while. So when we draw that scenario, you might need to be thinking about your trigonometry that we've been using. So like the cosine, sine, tangent, all those. So think about trig as you're drawing these force diagrams. Okay. And then when you're drawing that scenario, you also need to write down all that you know, all that's given, info that's given. And the hardest part, which it's very difficult to describe how to do this because this is kind of like a puzzle solving sort of skill. So when someone asks you to solve a puzzle and you solve a puzzle, it's hard for you to kind of describe how you solve that puzzle. So that's the last part here. And I've given you lots of problems, and I don't give you any kind of strange problems on the test that are different from what we've come through, we've encountered throughout these units. So there's no new puzzles that we need to solve. So as long as you've gone through all the problems that we've gone through this unit and review them and the ways that they are solved, you'll be fine. There's no new tricks that I've got up my sleeve that I'm going to ask you. So the last part is just to solve the puzzle. So solve the puzzle. So you're using what you've got, what you know about physics, to solve the puzzle. Sometimes it's easy, it's very straightforward. Sometimes it's not. You have to think a couple ways. You have to think through the problem a little bit more. It's kind of like chess, where you have to think about not just your first move, but your second and third move, and what your opponent's going to be doing as well. So solve the puzzle. That's the last part. So I can give you an example of all of these things happening here in a word problem, if you like. But before I do that, I'm going to tell you that what are the forces that we need to worry about here? The forces, you ask that as a question, what are the different types of forces and ways to approach them? Different types of forces. Well, that's all the forces that we've listed in the very first section of this, where you have friction, normal force, spring force. We don't really talk about that. Tension is when you have a rope. Thrust is when you have something that's expelling some sort of a gas, usually, or fluid. It could be water. And then there's gravitational force. So friction is probably the trickiest, and so I'll go through one of those problems right now. It involves all these ideas here. Vectors, trigonometry involves that. Write down all the given information that involves that. It involves these equations over here. Let's see. What's a good one to go through? Let's see here. Yeah, let's do this one. So this is a practice problem. It says a fire breaks out, and this is the practice problem on static and kinetic friction, that problem set, that workbook problem set. The practice problem number 1, a fire breaks out on a high-rise building and a rescue helicopter is brought to the scene. The rescue basket is lowered to the roof, and some occupants of the top floor escape to the roof and enter the basket. As the helicopter takes off, the cable momentarily makes a 78.2 degree angle to the horizontal, imparting a slight horizontal acceleration to the 621 kilogram basket occupants across the rooftop. The coefficient of kinetic friction between the basket and the top of the roof is 0.568, and the tension of the cable is 4,980 newtons. Determine the acceleration of the basket and the occupants. Suggestion: begin with a free body diagram. So what I'm going to do first is I'm going to say, okay, well, I'm going to try to draw this scenario here. So I'm going to take the basket, draw it right here. Here's the basket. It's just going to be like a big box. I'm just really, really simplifying this. And that's the center of mass. It's on a rooftop, and I'm going to say it's sliding this way. So what are the forces on this basket in this scenario? Well, if you, I'm assuming you have the problem in front of you. I hope you do. I'm assuming that there is gravity. Gravity is always acting in these problems. So gravity is coming straight down force due to gravity. There's a normal force because this basket is not being lifted up yet. So there's some force between the surface of the roof and the basket. So there's being pushed up. So there's a normal force going on there. But notice I drew it smaller than the gravitational force because I know that there's also a cable that is pulling this basket. And the cable makes an angle with the horizontal. So here's the horizontal, and the cable's pulling up this way. The cable's making an angle of 78.2. 78.2 degrees. And this is a force. This is a tension force or applied force or whatever you want to call it. We can call it a tension force. But we know what that is right away. It tells us 4,980. So I'm kind of combining both of these steps right here. I think that's a good thing to do. Okay, that's in newtons. I'm just going to assume that all the forces are in newtons, since that's what the problem does. Okay. There's also a frictional force here. So if this cable is pulling up this way, there's also a friction force that's opposing its motion. So we're just assuming that it's moving to the right here. So there's also a friction force going the opposite direction, which should be pushing to the left. So let's put that in there. So here's a frictional force opposing the motion. And the motion is going to the right, but these are all the forces that are acting on this basket. So to start this word problem, you just first draw the scenario. Think about trigonometry now. So the trigonometry, these are all perfectly up and down. This is left and right. Here, this frictional force is going exactly to the left on this horizontal rooftop. And we've got this cable that's pulling up here. at this angle. Now, what I like to do in all these kinds of problems when we have vectors, and you're eventually going to try to figure out how to add all these vectors together and figure out what the overall force is going in one direction. What I like to do is I like to simplify this, and I like to make this kind of angled vector right here. I like to break it into its parts, its components, in other words. So it has this x component right here, and it's got a y component right here. So this is the tension force in the y direction. I can say tension force in the y direction, and this is the tension force in the x direction. Now, you use trigonometry to figure out what these forces are. So I'm just going to do that right away because I know about this trigonometry and I've been familiar with this for a long time. So I'm going to say, all right, well, this force over here is 4980 cosine times cosine of 78.2. And I'm going to say this right here, since I've been working with these kinds of trigonometry problems before, I know that this is 4980 times a sine of 78.2. So I'm not even going to really worry about this up here because now I've broken that force into this and that vector. Now I've got all my forces in the x and the y direction, so it's perfect. So for these kinds of like friction problems here, the question overall is determine the acceleration of the basket and occupants. For these kinds of friction problems, there is a bit of a trick in the puzzle solving area here, and that trick is that you need to find the vertical forces first so you can determine what the friction force is and then use that friction force to determine the horizontal force. Okay, but before we get to that, I'm going to write down all the other information that we should know. And that's this little part right here. Write down all the info that's given. So, I've already written about the angle, the mass of the basket. That'll be important in a minute. The mass is 621 kilograms, and that's in our proper units here. And we know that the coefficient of friction, kinetic friction, is 0.568. Okay. And that's all, and this is also given to us right here. But that's it. That's all it's given to us. So in a problem like this, now we're on to this last step right here, solve the puzzle. And then I think this might be where you're like, okay, so what, Mr. Sand? We've got all the information here. What do we do now? Well, this is where solving problems over and over again, you start to develop sort of an intuition for how to solve the puzzle. You might have intuition about solving like a jigsaw puzzle. That's a really easy kind of puzzle to solve. You start with the outside edge pieces first, maybe the corners first, and then you start kind of looking around for all the flat edges. And then you start maybe thinking about the color. You look at like what the boxes, the puzzle should look like. You start to put together the pieces that look like they're similar colors in one area. That's sort of a strategy to solve a puzzle. There's also strategies to solve puzzles like this, these physics puzzles.